Next is a example of Bayes rules. So we describe it with an example. A factory has three machines: machine A, machine B, and machine C. These all three machines make the same item, and one day we use the machine A, other day we use the machine B, and the third day we use the machine C. And let's say machine A is used on 30% of the days, machine B is used on 20% of the days, and machine C is used on 50% of the days. And the chance of defective product with A is 5%, with B is 6%, and with C is 3%. I get a defective item. One particular day I get a defective item D. Now I want to know what are the chances that came out from a particular machine, say A. What are the chances that the item came from machine A? So let's think of a sample space. So we have a sample space which is basically divided in three, because you can either come from A, come from B, or C. This make up the entire sample space on a given day. When we say this is called as A, B, and C are collectively exhaustive and mutually exclusive. They are collectively exhaustive because they together conclude the entire sample space, and they are mutually exclusive also because it's either A or B or C. So A and B and B and C and A and C is 0. So now 5%, 6%, and 3% can be thought of a conditional probability getting a defect given a particular machine. So these are the conditional probabilities that given a defect, getting a defect given a particular machine. Now what is a probability that on a random day machine A is being used? That would be 0.3. And we want to know probability of let's just say B given a defect. Given that we have a defective item, what is the probability that it is B? Now here's the difference here, it's critical. Given that we have a defective item, what is the probability that it is B? This is different than probability of D given B, which is probability of a defective item given that it's a machine B, which we already know it is 0.06. So since sample space is this defective item sort of overlies this defective this entire sample space. Sample space is split into three parts. So defective item can be defect item and A, or defective item and B, or defective item and C. So this is the intersections of them. Since A, B, and C are mutually exclusive, these three intersections are also mutually exclusive. So if they are mutually exclusive, since they are mutually exclusive events, probability of D will be probability of D and A plus probability of D and B plus probability of D and C. Now think of this one for a minute. Probability of D the probability of D given A will be probability of D and A divided by probability of A. So probability of this is will be D and A times probability of A. Same would be the other one, probability of D given B times probability of B and probability of D given C times probability of C. And this is all probability of D we are trying to find out. So we want probability of, we want this one, probability of B given D. So probability of B given D will be probability of B and D divided by probability of D. But probability of D is already this. So we can put this here. Then probability of B given D becomes probability of B and D divided by probability of D and A plus probability of D and B plus probability of D and C, which are broken down into this and which we already know these things. Probability of D defective given A is 0.05 and probability of A is 0.3. Probability of defect giving C is 0.06 times 0.2 and this is 0.03 times 0.5. And this one also, probability of B and D is the same as this one. So overall it will be probability of B given D is 0.06 times 0.2 divided by this number, which is going to be 0.015 plus 0.012 plus 0.015, that is going to be 12 by 42 or 2 by 7.